So it's 12:15, and I welcome you to this session on data-driven methods for early design phases. My name is Tobias Larsson, and I'm a professor at Blekinge Institute of Technology, working mechanical engineering and modeling and simulation as my main research interest. So we are today going to take part of 5 presentations, and I will shortly introduce you to the presentations and the people behind it. It is pre-recorded videos that are going to be presented, so we are basically going to run all the videos after each other, and after that we will pick up on the questions you have posted in the chat. And since the authors are also with us here, the authors will of course have the chance to respond to these questions. So remember that the format is that you can either post questions in the chat that we'll pick up afterwards, or you can request to talk after. So the papers we have today, the paper number 1 is using machine learning for product portfolio management, a methodical approach to predict values of product attributes for multivariant product portfolios. It's being presented by Mehlstäubl, and he works as a research associate and PhD student at Institute for Technical Product Development at the University of the Bundeswehr Munich since 2019. His research topic is the use of machine learning in product development. The focus in on the disciplines of product portfolio and variety management. Previously, he studied mechanical engineering with a focus on product development at the Technical University of Munich. The presentation number 2 is evaluate similarity requirements with multilingual natural language processing. It's being presented by Ursina Bisang. She completed her bachelor's degree in applied computer science from Brandenburg University of Applied Sciences in 2018. Since then, she has been pursuing a master's degree in cognitive systems at the University of Potsdam. And since September 2019, she works at the IPK Fraunhofer. Her research interests are machine learning with a focus on natural language processing and explainable artificial intelligence. Paper number 3 we will listen to is a survey on the challenges hindering the application of data science, digital twins, and design automation in engineering practice. Simon Rädler is currently a PhD student in computer science at the Vienna University of Technology, and the one presenting the paper today. Simon's research interests lie in the area of digital engineering, more specifically in the development of methods to support the integration of machine learning into early systems engineering approaches using model-based techniques. Paper number 4 is Generative Pre-trained Transformer for Design Concept Generation and Exploration. This is presented by Xiao Chu, who is a PhD student at the Data-Driven Innovation Lab of Singapore University of Technology and Design. He received a bachelor's and master's degree in industrial design from Sichuan University. Xiao has a firm background in design methodology and is very experienced in industrial design practice in the industry. His research interests include data-driven design and specifically in applying AI techniques for design concept generation. The 5th and final paper is Success Factors for the Validation of Requirements for New Product Generations, a case study on using field-gathered data. This is being presented by Stefan Wagenman, who started his PhD studies in late 2021 at the EPEC, Karlsruhe University of Technology. For the course of the PhD, he is cooperating with Trump Machine Tools. His research focuses on enabling the systematic use of usage data from previous product generations in development process, with a special focus on the validation on the system of objectives. So these are our 5 presentations, and as said, we will now listen to the videos, and do remember to post questions in the chat. Please, Jelena, run the videos.
Hello and welcome. My name is Mehlstäubl. I'm a research associate and PhD student at the Institute for Technical Product Development of the Bundeswehr University in Munich. Today, I would like to present you our approach, our methodical approach to predict values of product attributes for multivariant product portfolios. First of all, I would like to say a few words about our motivation. In the last decades, we had an increasing demand for customized products, and this in turn leads to a higher portfolio complexity. We have in many companies, we have countless variants, and these variants are really connected to each other. We can see in our, for example, ramified bill of materials. On the other hand, in product portfolio and variety management, the processes are still very manual and experience-based. There we have a lot of challenging Excel files and a lot of experts who define rules to handle this complexity. But the manual and rule-based expert systems can not longer handle the complexity, and we need more intelligent and data-driven solutions. The challenge of predicting product attribute values is that we have in product development, we have different views on a product. One view is the customer feature view. It's in industry, the customer feature describe the target characteristics and properties. Characteristics are the characteristics can influenced by the designers by themselves, and the properties results from the defined characteristics, like for example the performance. And during a configuration in multivariant products, a customer selects the customer feature he wants. Today it's often in many industries with complex products, we have a lot of features from 100 to 1,000 features the customer can select, and normally no product is developed twice or sold twice. In synthesis, the designer defines the product components in the component structure. The component structure describes the actual characteristics, and in analysis we determine the actual properties of the final product, and that are the product attributes we want to predict in this approach. Today, normally we have to, during the configuration, we also have to estimate or predict the product attributes of the new configuration we never have built before. And today we have a lot of rule-based expert systems who define these product attributes. There we need a lot of expert knowledge to define the rules. The rule definition process is really time consuming, and often the results are inaccurate. In our approach, we want to do this with the analysis of past data, of past vehicle configurations, and the associated product attribute with machine learning. Now I come to the research question. First research question is, how can values of product attributes of multivariant product portfolios be predicted based on new customer feature configuration using machine learning, and what advantages can be achieved by using machine learning in this use case? Our methodical approach is based on the CRISP-DM process model. First of all, we define the goal and select the product attribute. After that, we define the data structure which is required for the use case, and then we start a data cleaning transformation, and depending on the attribute, we do a regression or classification analysis and evaluate at least the results. There you can see the basic architecture of the model. On the left, the input is the feature categories, and to every feature category we have one customer feature. Depending if it's a continuous variable, we use a regression, and if it's a categorical variable, we use a classification analysis to predict the output, the product attribute. We already did it for the vehicle weight. For weights of a product, we used trucks, for example, with our industrial partner, the payment willingness, the CO2 values, and the country of sales. Now I will go a bit further to the results with the vehicle weights. Here you can see a table with the results. You can see on the left side the linear recursion and support vector machine delivers inaccurate results, but if you go to the right until the neural network, we can see the results are really promising. We have an absolute error with 33 kilogram and what is in percentage error from 0.6%, which is much better than the rule-based systems we have today. There we have about a percentage error from 3%. Moreover, the prediction time is much faster, and the process of the definition of the rules is also faster or less time consuming. There you can see the visualization. We also have a few outliers. We analyze them further, and then we can see that it was not really an outlier, it was a mistake in the data. The real value in the data was 8 tons, and the predicted values was 12 tons. And we also find another configuration from the same customer with also with the same identical configuration, which has 12 tons. There we can see that our model predicted the result right, but we had a mistake in the data. At the moment, we implement the method or the methodical approach in a prototype. There you can select the different product attributes, the machine learning model, and load a configuration or give the number of the configuration a customer already ordered. Then we can show or export the results, and there we are ongoing at the moment. Then I already come to the end of my presentation. Thank you for your attention, and I'm looking forward to your questions. Thank you very much.
I would like to present our paper, Evaluate Similarity of Requirements with Multilingual Natural Language Processing, that I wrote with Jörg Brünnhäußer, Pascal, Lünnemann, Lukas Kirsch, and Lindow. This presentation is divided into 4 parts. First, I'll illustrate the reasoning for using natural language processing to process our requirements. Next, I'll give you an overview of our approach, and then I'll outline our results, and I'll finish with a discussion of these and an outlook. Gathering high-quality requirements is crucial for the success of a project and designing a good product. This faces many challenges. For example, natural language is ambiguous, so requirements are sometimes phrased redundantly or contradictorily. A project can contain a huge number of requirements, for example, hundreds of thousands per project in the automotive industry. Requirements management is very time-consuming because it's mostly done manually. And multinational companies additionally have requirements in different languages in the same project, which increases the complexity of handling them. Automating the processing of requirements reduces the time and cost of processing while also having the potential to improve the quality of the processing. Our idea is to support the person processing requirements by finding semantically similar requirements so the person can decide whether these are redundant or contradictory and can take care of them. We use 2 different datasets, the in-domain data consisting of 165 requirement pairs, which were taken from the documents in the peer corpus, and the requirements were paired by us according to Similarity. And while they were originally only in English, we human translated them to German, which was aided by machine translating. The out-of-domain data contains 300 general sentence pairs that were randomly selected from the XNLI dataset. And originally, this was only English data, but then it was human translated to German by the original authors. The pairs in both datasets were annotated for semantic textual similarity, which allows to label sentences on a scale from these sentences are almost identical, just using different words, to these sentences aren't even on the same topic. Our approach consists of 3 steps. First, we prepare the data by searching for it and extracting it, translating it where necessary, and annotating it for the semantic textual similarity. Next, we use our 4 models to generate embeddings. We have 2 word embedding models and 2 sentence embedding models. Word embedding models turn words into vectors, where more similar words lead to more similar vectors and less similar words lead to less similar vectors. Sentence embeddings do the same, but for sentences as an input. FastText is a monolingual word embedding model, so it's inherently only able to work with one language, in our case English, and we use Google Translate to translate our German language sentences. XLMR is a multilingual word embedding model, and KDSIM and KDPAR are both multilingual sentence embeddings. The multilingual models are able to work with both English and German without a need for translation. Next, we use different similarity measures to generate similarity scores for our sentence pairs from the different data sets. First, we need to aggregate sentences that were embedded with word embeddings. We do this with either the mean or the smooth inverse frequency, some kind of weighted average. And then these sentences can be compared, or these sentence pairs can be compared with cosine similarity. Alternatively, the word movers distance can be used for sentences that were embedded with word embeddings. And for the sentence embeddings, we use just the cosine similarity on the sentence vectors. To compare our generated similarities to the gold labels of the semantic textual similarity, we use Spearman's rank correlation. Our results can be seen in the graph on the right-hand side. It contains the average Spearman's rank correlation of the in-domain and out-of-domain data. And KDPAR and KSIM both perform best. They have the highest Spearman's rank correlation between prediction and labels. XLMR with a smooth inverse frequency as averaging and the cosine similarity for comparison performs quite well too, although with the mean it performs worse. FastText perform worst of all embeddings compared especially for the settings that contain German sentences. They perform better with a smooth inverse frequency and the word movers distance than with the mean. On this slide are the results for the in-domain data and the out-of-domain data separately. On the left-hand side is the in-domain data, and on the right-hand side, the out-of-domain data. Some bars are almost transparent. They have a too high p-value to be considered. Both KDPAR and KSIM perform well for both data sets. XLMR performs better for the in-domain data, and FastText performs sometimes better for the in-domain data and sometimes better for the out-of-domain data. What is noticeable is that FastText performs much less variably when it's used with the out-of-domain data. A short discussion. KDSIM and KPAR both perform consistently and well over both test sets, and they perform well enough that they can be used out of the box. So they are our favorites. XLMR with a smooth inverse frequency performs quite well too, but rather variably. Maybe the smooth inverse frequency is less suitable for the context and embeddings like XLMR, as it was originally created for non-context and bare embeddings. XLMR performing worse in the multilingual sentence embeddings might be because it's better suited to fight direct translation than similar sentences. And for the in-domain data, FastText is much better in the English setting than in any one containing translated data, while in the out-of-domain data, this difference is smaller, which leads us to believe that requirements are harder to translate with Google Translate. Maybe they are too specific or not cleaned well enough, or maybe they contain too long sentences. And all of these findings could be made more meaningful by using more test data or by letting more annotators label the data. Last short outlook. While the sentence embeddings perform well in this paper, they perform better in the original paper, and this might be remedied by fine-tuning them on requirements data. The multilingual sentence embeddings combined with the cosine similarity could be deployed into Contact Elements platform. This is a product design platform that is offered by our partners at Contact. And this would allow us to prove our theoretical results in practice. And our data was only in English and German to quite similar languages, and all sentences were direct translations. So it would be interesting to see whether using less similar languages and requirements that were written originally in different languages can change our results. And last but not least, these are the papers cited in this presentation. They can also be found in our paper.
Welcome to my today's talk about a survey on the challenges hindering the application of data science, digital twins, and design automation in engineering practice. My name is Rädler, and my co-author is Eugen. The agenda. First, I will give definitions on the terms data science, design automation, and digital twins, because different understanding of these terms can be observed. Survey design and response will be the next part, followed by the results, discussion, and finally conclusion, remarks, and future directions. Design automation refers to the computational methods to support design tasks such as configuration solutions or CAD macros. Data science refers to extraction of information and knowledge from unstructured and structured data to enable, for instance, prediction or maintenance. This is also known as data mining or machine learning often. The digital twin is a digital representation of a physical object focusing on the exchange of data, simulations, analysis, and optimizations. Digital twins are often referred to as, for instance, CAD files, but a CAD model is a digital model, so a virtual representation of the physical part, but not an entire digital twin. Our survey is split up in two parts. The first part is a quantitative survey executed as online question with mainly closed answers and Likert scales. 81 responses out of these 1,842 contacts participated in this online questionnaire, which results in a response rate of 4.4%. And we used the focus group interview to bridge the interpretation gaps from these online questionnaire. Over 50% were head of department or C-level because we required an overview of all the company projects and not deep insights into specific parts. 2 out of 3 participants submitted comprehensively, and about 60% or between 60 and 70% of the participants were interested in these technologies. Our results showed that 1/4 are about to using it in a daily operation, one of these techniques, and about the half are in a pilot or a concept phase. 1/4 is trying to implement or trying to introduce a pilot or a concept within the next 5 years. The main motivation for the companies were to reduce the errors, optimize solutions, ensure quality, and reduce lead time. As it can be seen, the motivation for the different parts are slightly different. And interestingly, the reducing of the cost is not one of the top 5 reasons to use these computational methods. The results showed that the effort for the implementation from proof of concept to production is the main challenge, followed by the knowledge in the company, the data quality and availability, and the unclear benefit. Somehow the knowledge of the experts in the companies influence the other challenges, because if an expert has more experience in implementing, then it's less effort or the duration will be reduced. Even if the companies are aware of we need more experts, it's hard for them to find experts on the market because the experience of the companies is that there are no experts or no qualified experts with a lot of experience on the market. But even so, there are no experts on the market. If the companies are implementing such projects, then the return of investment is valuable and the acceptance of the employees is very high. Despite the knowledge is not available in the companies, the expert knowledge is the main criteria to select an algorithm, for instance, in data science, followed by try and error approaches using pre-implemented algorithms from the internet. The methods which are available for implementation support are not often used, which might also originate from they are not aware that these methods exist. So the lack of knowledge is the main challenge. Experts are not available on the market and methods are little used in industrial practice. Therefore, we might think about if universities require to change the education of engineers so that they are more aware of computational methods and can implement parts of these computational support. More industrial case studies might support the trust in methods, and therefore the application of methods will be increased. The methods also required to support non-experts and not just dedicated experts in a specific area. So methods for data scientists have to be applicable for engineers as well. And the integration of computational methods into frameworks such as enterprise architecture might support the implementation and integration effort, because enterprise architecture supports the current infrastructure and get an overview of the softwares available in the company. Main hindering obstacles are reviewed. The focus of motivations is reducing errors and ensuring quality. And even so, there are challenges in the companies and they are aware of these problems. Companies are still interested in these technologies within a short period of time. Our future work will consist of developing methods to support the integration into an existing and future infrastructure by leveraging enterprise architecture methods and knowledge acquisition and implementation support for non-experts. Thanks for watching this talk.
Dear fellow scholars, I am Hao Zhu from Singapore University of Technology and Design. Here I present our recent work of generative pre-trained transformer for design concept generation and exploration. In conceptual design, designers must generate a wide range of concepts during the divergence stage before convergence can be made. A concept generation method or tool can play one of the three roles: as a guide, as a stimulator, or as a generator. Guide-like brainstorming is instructively involved in the generation of design concepts, providing design rules or guidelines. A stimulator provides inspirational stimuli to provoke designers to conceive new concepts, like design heuristics to support design thinking and the knowledge system to provide extended knowledge. Generator is an automated computational agent that creates new concepts for the interest of designers, which is the focus of this work. Concepts can also be represented in different forms. Abstract diagrams like functional model provide precise connection and relationship between terms, but can be too abstract to interpret. Spatial visualization, on the other hand, is a form detailed to the spatial relationship between parts or the geometry of a certain part, which has very much been fixated. Concepts represented in verbal texts can balance for abstraction and fixation, providing understandable and flexible concepts for early design stage. In the taxonomy developed in this section, oral approach is positioned as a concept generator which creates concept description in natural language, using the technology of natural language generation. Natural language generation, or NLG for short, is considered as a computer program that generates natural language as output. Common application includes machine translation and paraphrasing. Generative pre-trained transformer is a series of language models which has been popular in NLG. They have been pre-trained with a very large dataset of textual information, and they can use knowledge and logic learned from the data to deal with language-related tasks. GPT-2 uses the two-step training strategy of pre-training and fine-tuning. The pre-trained model can be fine-tuned given a customized and task-oriented dataset. GPT-3 is trained on a much larger dataset containing 400 billion tokens. It is capable of future learning, where the model can learn from only a few examples of the NLG task. Our experiments of design concept generation using GPTs were conducted on the web-based server of Google Colab and OpenAI API. The dataset consists of design descriptions of over 14,000 Red Dot award-winning design from 2011 to 2020. Knowledge for the task is provided through the dataset used for fine-tuning the GPT-2 or in the examples for field-of learning of GPT-3. We take invalid input as for conditional learning. The input should be customized for specific reasoning we want the model to learn. In the experiments, we explore problem-driven and analogy-driven reasoning with different settings of conditions and transformer models. In the customized task data for problem-driven reasoning, the category of the design is stated at the beginning as a condition. The problem is stated in the first sentence of description, followed by the solution idea. This structure is common in problem-driven design and ideal for GPT to generate a solution in response to a problem. However, not all award-winning designs are problem-driven, and often the description does not include a problem. Our hypothesis is that the model can learn from those problem-driven design in the dataset to execute problem-solving tasks. In this experiment, we fine-tuned a GPT-2 base model for 14,000 steps and tested it with 2 program statement input. 2 concept generation examples are shown here. One uses a problem appeared in the fine-tuning data, showing the model's capability of generating varied solutions given the same problem. The other uses a new problem the model has no previous knowledge about, showing it is also good at solving new problems. As there are insufficient design by analogy examples to fine-tune a GPT-2, the analogy-driven reasoning experiment employs 5 design by analogy examples selected from the red dot dataset for field-of learning. A structured sentence specifying the source and target domains is inserted before these samples so that the GPT-3 may learn to develop ideas based on the input conditions. Here we present 2 drawing concepts generated by GPT-3, drawing analogy from the given source domain of lantern and origami. The model successfully understands the source domains and applies the lighting features of the lantern and the folding mechanisms of origami. The generated concept learn to build a clear analogical mapping between the source and target domains, even if the 2 given sources are culturally related and very distant from the technical domain of drawing. This is because the GPT-3 is pre-trained on a massive dataset that includes nearly all possible kinds of scenarios and syntax, and a few examples are enough to evoke the specific reasoning it has learned. This work proposes a concept generation method using generative pre-trained transformer. Designers who use the tool may discover valuable ideas that are beyond their knowledge base. They can also draw further inspiration and make it more suitable for their own project scenario. Evaluation matrix is required to assess generated design concepts. Common NLG evaluation matrices, such as BLUE and WMB, require ground truth samples to measure the distance between tags. In design concept generation, we aim to evaluate the usefulness and novelty of any individual concept, where ground truth benchmark is seldomly available. Furthermore, this work may possibly be integrated with other approaches for a broader variety of applications, such as knowledge network, which can be used to extract sources for analogy. This concludes my presentation. Thank you very much for listening.
Hello, ladies and gentlemen, and welcome to our presentation today. My name is Stefan Wagenmann, and we're going to speak about the success factors for the validation of requirements for new product generations, where we carried out a case study on using field-gathered data. Requirements for new product generations are derived indirectly from information regarding the use of reference system elements in the customer production. Therefore, information has to travel from the machine operator level via multiple stations like sales, product management, until they finally reach the developers themselves. The described information management process results in a silent mail principle, which results in the loss of information. Using data from reference system elements has therefore high potential to overcome the silent mail principle. Product generation engineering describes the development of new systems, where each system development is based on a reference system defined by its subsystems that already exist or are under development. These could be design models, requirements, or information from validation processes. So new systems are developed on the basis of the reference system through the combination of carryover, embodiment, and principal variation of subsystems. Some companies already collect vast amounts of data. Most of them do not use data actively to develop new products, though. New technologies such as data mining allow developers to get deep insights into generated data sets, which carries a high potential to support the decision-making in the development process. Nowadays, data is already used in many different aspects. In the context of mechatronic systems, vast amount of data could be generated, technically speaking. We use it for services, performance monitoring, benchmark simulations, and in our case, the analysis of the reference system, where we lay on a focus on. The research is structured by the DRM Design Research Methodology after Blessing and Chakrabarty, and we focus here on the DS1. The target of the research is the identification of success factors for the data-driven validation of requirements for new product generations. Here we answered the questions: which activities are necessary for the data-driven validation of functional requirements in the development of mechatronic systems, and what efforts are they associated with? And secondly, which success factors can be identified when analyzing usage data of reference system elements for the development of mechatronic systems. One example here could be how often is compressed air used for laser cutting. So this was a pretty recent example where the expert said, okay, listen, we need this function in the machine for the customers because it's really important for etc. reasons. And we did the analysis. We had a look at the reference system, and the results told us, okay, only 0.57% of the jobs are programmed with compressed air as a cutting gas, which basically means there's a huge delta between what the experts told us and what the data says. During that time, the belief was that it takes around 1 day to carry out such kind of analysis. We showed that the average time to carry out such analysis is around 3.5 weeks in development practice. So we see the similar picture of all 5 carried out use cases, where basic work and interdisciplinary work account for the most effort taken per case, followed by programming and checking results. More in detail, the basic work is described as developing the analysis specifications, just as the logical combination of parameters, and the activities for initial testing of the data quality. On the other hand, the interdisciplinary work accounts for the effort taken to access data tables, for the time the experts take to come back to you after you ask them a question, and due to the complexity and the novelty of the topic, there's a great deal of effort required. Here we also see a strong dependence on the type of questions and the requirements that are addressed. What the graph on the left side doesn't really show is that the process is iterative, what we see on the right-hand side, because we start with the basic work, talk with experts, start programming, get our first results and see, oh, there's some fault, go back to the basic work, and so on and so on. And an iterative process starts building up, where we slowly walk our way to a good solution. So speaking about success factors, what does it take to execute such analysis? On the one hand side, you need the knowledge about the machines and the functions. You need to deeply understand the technicalities of the objects under investigation. On the other hand side, you need the competencies for performing such analysis, as well as the knowledge about the data structure and the data origin. The data origin here strongly correlates with the acceptance. We saw in the study that in the early phase, people weren't sure about the context of the data origin, so they didn't trust the data. There was a high skepticism. And then we introduced a disclaimer where the context of the data generation was described in detail. And after that, we saw a rise in the acceptance of the analysis results. Additionally, the data quality plays a big role here because the assignability between data points and the consistency of the content of data points to real products is a central aspect for the analysis against the background of the resilience of analysis results. In future projects, we will carry out more of these case studies, and the goal is to develop a process model that will support developers in the use of data for validation purposes. Here, I want to take the time to thank the German Federal Ministry of Education and Research for funding this project, and the project management agency in Karlsruhe, which supervised the project MOSES, Human-Oriented Design of Complex System of Systems, in which context this research has been done. I thank you for your attention, and I'm happy to hear your questions now.
Excellent. So that was our 5 presentations. I think we have some minutes for basically questions on each of these presentations. And I will actually start out with the presentations for the questions for the first presentations by Jan Mehlstäubl. And we have one here in the chat, so I think you have also read it. But we start with the first question from James here around, I'll just repeat it if not everybody's reading in the chat. James Gopsil is saying, really interesting results. I was wondering if you could give us an insight into the development time on performing this analysis and an anticipated return of investment. Is it an approach that is repeatable for other metrics you wish to generate?
Yeah, I can say a few words about the development time. From the point we got the data to write the code, that means to prepare the data and train the model, or to write the code to train the model with the different algorithms, we need maybe about 4 weeks, or I need about 4 weeks. That means it's really fast. If you go there with a bigger development team, it would be much faster. But to say something about the return investment, it's really difficult because we don't have a software we sell, or if we go to one product attribute, it really depends on the product attribute and the value it brings with it. If I go to the example for the weights, before at the moment, our industrial partner, they write rules by experts. That was a process about a few months with a team of experts in the weight prediction, and there we are much faster, don't need that much money to implement it, and there we had already or have already a return on investment, I would say. But yeah, at the moment we are struggling a little bit with at our industry partner with the user interface and to deploy it there for the daily work, but it's more a bureaucracy thing. That means in a big industrial company, it's more bureaucracy than development time. If we implement it as a startup or something without these restrictions, it would be, we could do a prototype maybe in 4 weeks. And it's repeatable to different metrics. The code is really standardized, and we only have to change a few things for a new variable. We only need the configuration. The configuration, that means the codes of the configuration, and then enough training data for the product attribute, and then we can train the model and do our predictions.
Excellent. I guess you read a response at the same time from James here. There was also a question from Radisic Aberg here. Did you do a comparison to rule-based method, as all configurations and components ways should be digital available and the resulting product is described by bill of material? Wouldn't it be easier, quicker to simply cross-reference the bill of material with the weight of the component and sum it up?
I often get this question. first, the weight is only one example or one evaluation of our method or our code, but also the weight, it's not that easy because a lot of companies are not digital consistent in their configuration process. This is the one thing. And the other thing, especially with handling trucks or also cars, you have a lot of components like cables or tubes. You cannot or it really changed there with the length depending on the configuration. Also the weight is changing, and normally you cannot directly say how the weight is. It's different on other kind of components, but especially cables and tubes are really difficult to predict.
Excellent. I don't know if there is anybody who has another question to pose, either through audio or through the chat. Otherwise, actually, John, I have a question. I mean, you were saying also in your paper that you are looking at testing non-technical product attribute values. How would you go about testing those non-technical values?
We did it, for example, for the payment willingness of the customer. If we go to our industry partner, they define a price based on the feature configuration. Then they have they change the price depending on the country, but in the end, depending on the customer, we also get a change in the price, and there you cannot really, also the price is calculated by the feature configuration, but it's changing depending on the customer in the end. Sometimes how many products the customer is buying, or how big is the company, and there in the end you cannot say how much a customer is paying for one customer feature. And we also try to figure this out and predict the payment willingness for configurations. It's more difficult. The results are not that good, but I'm not sure if I answered your question, but that we understand on non-technical product that we did something like payment willingness or what's not really fixed with the product.
No, I get it. Okay, thank you very much. There might be more questions coming back to you, but let's move over also to second paper. Thank you, Jan. The second paper presented by Ursina. I don't know, Ursina, if you read the question by, for example, if we start with a question from Gaetano, do you read it in the chat? It was a question on if you're using the semantic relationships between terms, not just synonymy, but also the other nymis that has a key role in describing the complex systems. And if so, in case, what sort of resources are you using? If you could give a response to that. Let's see if I can see if we have the chance to unmute. Jelena, you have the possibility to see if we can unmute Ursina.
Unfortunately not.
That's crazy.
Dear Ursina, like, could you maybe refresh the whole session with F5? Maybe it helps.
So we give it a second. Let's see if she comes back. Now it works.
First question about semantics. We didn't use anything explicitly semantic. We only used the information that's implicitly inside the word embeddings. So yes, we use semantic information, but there is nothing to share about it besides the word embeddings we used or sentence embeddings. And
I don't know, Gaetano, is it there? Do you have a follow-up question on that, or we'll leave it by that? Okay, Gaetano seemed happy. So there was also another question from James here also. And I read it. Your approach appears very flexible in a number of techniques one could use at the different stages. It would be interesting to know how a designer would be affected by the results given by different approaches. How sensitive is a designer to the results from the different configurations of your approach?
basically, the idea of our approach was to find the best approach, at least compared between the things that we compared, so that a designer would not have to decide anything about that. So I think it will not influence a designer in his or her work, but different approaches could, of course, influence the outcome. So, for example, if the methods are not really good at finding similar requirements, the designer's work would probably be harder because it would be harder to spot requirements that are too similar and should be either combined or maybe also that have a disagreement and should therefore be dealt with. Does that answer the question?
Okay, thank you. So, any other questions around the table?
Yeah,
I do have a question here, Ursina. So, I mean, if you want to kind of test or validate this approach in a real design situation, what would be your next step then?
I mean, it would probably be to implement it in a tool and see how it is for people to work with it.
And how many steps is it to build this into a tool?
I mean, that depends on the tool, but probably not many. At least if we take the sentence embeddings out of the box, they are trained, they are ready to use, also license-wise. So
okay.
Would probably be not many.
Okay.
But yes, I also agree with James in that chat. It would also be interesting to see if a designer would be interested in choosing the configurations themselves. But we didn't do any experiments on that.
Yeah, I could see the value being in the experiments because that's the only way you test it, I think.
Yeah.
Okay, thank you for that, Ursina. Let's move over to presentation number 3 by Simon Rädler. So I think there was, let's see here if I scroll up. So also here we had a question to start this off from James. Some interesting findings that support the transdisciplinary transformation of our industry. Bringing more disciplines together to design is a really interesting challenge for a community. So it's kind of a reflection. So what's your opinion on that, Simon?
Yeah, many thanks for the comment. I also think that the main challenge is to bring the knowledge in the different disciplines involved in these data analytics and data-driven methods, such as data-driven engineering or so. And I think we should focus on, so to hand over to the second question of Stefan, I think we should focus on elaborating methods supporting engineers to identify real use I observed in many talks to companies that they are more focusing on the technology. So like we would like to have a solution with data mining or data science methods. But in fact, the companies should rather say, okay, I would like to solve a specific problem and which kind of technology is really applicable. And then the next step is how can we support from our scientific perspective the industries so that they really can apply our methods that we are developing. And therefore, I think one of the challenges or the main changes that we should think about is how can we support industries, companies, and especially experts from different fields to apply basic data analytics. That would also support the trust in the data, which we heard today, I guess, in the last talk. That is a kind of problem for non-data scientists, or somehow also for data scientists.
Stefan, you were also posting the questions. Since you are in this dialogue, I think you could elaborate a little bit or follow up on that.
Yeah, I find it very interesting that we have the similarities. What I feel is that on the one hand side, we need to support engineers for allowing them to do data analytics. This is the one side. And the other side is that we have to lower the obstacles which are given by the infrastructure and organizations. We cannot say, okay, we give engineers now methods and tools, but on the other hand side, the infrastructure, like all the data availability in data warehouses, the applicability of easy Python scripts or something like this. Even Python scripts are, for most engineers, are not valuable tools. It has to be much more easier for them to really use data. I mean, in this room here, most of us probably know that storing and having data available is pretty expensive. And therefore, speaking about efficiency in a company, from my perspective, we need as many engineers to use data for their own questions, for their own development questions.
And a short comment on the post of James in the chat that we probably have to translate the problems in domain-specific language. Just to give a little bit of outlook from my research, I'm currently developing a method to formalize these machine learning tasks in systems engineering language, SysML, so that an engineer really can formulate the problem he's facing and further with model transformation derive executable Python scripts. That will be my future interest. So it's kind of aligned with James. Thanks.
I agree with James here. That sounds really good. And there are several sharing the same interest, apparently. Thank you for that, Simon.
You're welcome.
And let's move over, I think, and see. I haven't seen Xiao Shu present in the meeting. So I'm not so sure that we can have any questions on paper number 4. So unless it shows up, I actually think we would move to paper number 5 for questions. And that would be Stefan. And it's James opening up there also with a question of interesting results on the level of effort required. We need to appreciate the time it takes to perform the analysis, and can we map it back to the value of the results and whether it aids better decision making? Is it worth waiting for the results or going by instinct? So this is a classic question with all things computer, I think. So what's your response there, Stefan?
Yeah, that's some really good questions. Let me go one by one. The mapping the value of the results to the time taken for the analysis strongly depends on what kind of analysis we're doing. this mostly comes from if we have knowledge on the object under surveillance beforehand, it's much more easier to carry out such analysis. So we see a drastic difference in analysis of new systems, where we first have to figure out which data we can, data is provided and we can use in which context. And on the other hand, we see a strong dependence on the complexity of the questions. What most of the time happens is that the first questions always has to do with the basic usage of any function. Like, is function xy used in the machine by the customer or not? So it says, okay, around 0. somewhat percentages the customer uses the function. And the next few steps are then, okay, which technology is used and which materials are used for specific jobs. And then we go down like a cascade of questions, where we most of the times end up in the clustering of customers. And also, which is also outlined in the paper itself, is that most of the times we have to stop at stage 1 or 2 because there's no data available to answer specific questions. This is also one big point with what I mean with the changes in organization. So we have to have mechanisms which allow the developers to say, okay, listen, I'm now at the point where I need some kind of data, and I'm pretty sure I need it in 4 years also, because there comes a new product generation. Please now store it so that I can analyze it in 4 years. Because with the data, it's always the same. If you don't start collecting data at point t-1, you can't do analysis at point t. The second thing is that it aids to decision making. So what we saw is that we cannot use analysis as pure sources of only sources of truth. So the analysis has to function as the basis of a discussion. So with one example I gave in the presentation, where the expert says, okay, almost every customer uses the function with compressed air cutting. He said, okay, everybody uses it, but in reality, it's much more like that. Most of the functions aren't really used that often, and people tend to trust the anecdotal or the opinions of the experts much more than the data analytics. And providing analytics helps there a lot to get their discussions in the right direction. And for the last question, is it worth? Especially thinking of the concept of the PGE, we see that we have not only one development project, we have several development projects coming also in the future. So what we do now is we store our done analyses with all the parameters, etc., and create dashboards whatsoever. And then we connect the links to the dashboards with the requirements in agile web tools or desktop tools. And so it takes 4 weeks to carry out this analysis to create these dashboards. But in further product generations, it only takes one click on the link to see the new dashboards. So this is a process where we have to look at the long scope, not just for one analysis. So if the data is basically always up to date, we can use the links to the dashboards again for the next product generations, which in my opinion is a huge benefit for it. Yeah. And what was also pretty interesting, maybe we didn't stop doing these analyses, these use cases, and we learned a lot in the past few months, and we could probably decrease the time it takes maybe 1/3 something. And there will be some studies we will publish also from this. And yeah, stay tuned.
So, I mean, I find this highly interesting. I mean, the session is on data, and of course, we believe that we can find a lot of insights from data, with or without context. But one of the reflections I make also back, and I think this is a little bit on paper number 3 by Simon. So a little bit of question back to you. because you're challenging the kind of curricula of engineering education and engineering practice. Of course, with new methods, we want to put more things into the curricula. But if we look at this topic, what do we take away? I mean, you can't just put more things into an engineer's education, or otherwise we have to spend our entire life learning without going into practice. So what would you take away from engineering education today that is from, let's pose it as a radical question, which is useless knowledge to have an education today then?
Yeah, sure. That's a really hard question, and it's true we have to put things away. I mean, I'm not a mechanical engineer, therefore I'm not in charge of deciding which is not relevant. But I've heard from friends of mine that they practicing a lot of designing gears, for instance. But in the daily business, the designing of a gear or the modeling of a gear is actually not a thing that is so complex than it was 20 years ago. But to be honest, I cannot answer this question properly because I'm not a mechanical engineer. But if someone here is from the mechanical engineering department, it would be great to hear.
I would kind of agree with you there that you have to take away something, and some of the basic things from a general engineering education you could probably take away, and some of the physics and other items too. So around the table, anybody in engineering who would weigh something? John.
Yeah, I would like to say a few things about that from Simon. I also see that by our industrial partner that most of the engineers, mainly the older one, don't know anything about data science or machine learning. And yeah, I'm a mechanical engineer, and if I look back to my studies, the first 2 years was a lot of calculating by hand and drawing things you do today in a company with tools. You have your CAD tool, you have your calculation tool, simulation tool, and we do everything by hand. I mean, it's good to know how the things work, but I think it's too much. We should go more digital, more learn digital and intelligent stuff. I think every mechanical engineer should know how data science or machine learning is working. And there's also the problem in companies. I think it's not. I often hear that they don't trust in the results of machine learning, but I see that it's more they do their daily work, but then they start to define rules how they can solve their problems by their experience, because they don't know what machine learning can, and they don't know when they could use it to improve their work, and that's the big problem. I think everyone should have an understanding about these methods and these approaches to identify use cases in their daily work, and to know how they can use it and gain value from it.
I find this being highly interesting. I mean, looking at from the very, very rational view that maybe machine learning and AI, of course, can replace some of the what called simple knowledge that the engineers don't need to be taught. They could be taught problem solving instead, and then having code snippets to help us out in designing things. But one of the questions that apparently arise also, which I think Ursina touches upon, when you're talking about language, I find it highly interesting because when you start using these codifying schemes, we have to talk about the same thing, but we're using different language for same things, and ontologies and definitions. Why are we having different languages on Earth when we all could be speaking the same language, whether it's math or coding? So Ursina, how do you see that from the perspective here? Is it possible to have, let's say, one language to understand all these design principles or problems?
I don't really know, and I also don't know whether, I mean, from a design and engineering point of view, it's probably good to have a unite or like a combined language that everybody understands and everybody uses in the same way, but maybe that might also constrain, as in if other people express concepts differently, maybe they also come to different conclusions about how something should be designed. So I think there is value in unifying the language, but also value in keeping it diversified. And I think, as you mentioned, ontologies or knowledge graphs and these kind of like machine readable tools are probably a good way to unify knowledge, while natural language should probably be kept diverse. Like, and I think it's also hard to unify that worldwide, as languages are very diverse and people are very diverse. So I think it would be hard to completely unify that and to get everybody to agree on using like in a design to use everything exactly the same way in a design context.
I mean, we basically talk about two different things, but they are related. I mean, we want to have language to be able to have color and creative discussions, but when we speak into a computer, it's kind of practical to basically have a shape which each computer can understand, basically the coding. So I think this is not a new question, I think, but it's still a highly interesting and valuable question.
Yes,
so we have a couple of minutes, so I don't know. It's an open-ended question from my side. Can you have data and store it away and pick it up 10 years later and work with it without having the context around how that data was created? Might be a little bit a question towards Stefan, I think.
Yes, this also, the thing is that when you wanna like guide your organization to a data-driven development, you also have to work on which data do you provide to your designers, to your developers, and how is it provided, in which way, from over which channels. And over the years, this definitely will change. Some data will not be virtually sent on, some might add to the data store. I think that the data, the context of the data origin, the data generation, is like a very critical part nowadays for like implementing data analytics in engineering, because people have a low level of trust in the first place in analytics, and understanding the context of the generation of data is always necessary. It's not only necessary in data analytics, it's always necessary, but we as humans, we accepted it, that development now works as, okay, we have some experts in the development and they are working in the company since 30 years, so we don't question their perspective, and that's how it goes, and this needs to change.
That's true. I think I've seen data being thrown away just because you don't know how it was collected.
Yeah.
So Simon, might have a response there.
Yeah, I mean, this trust in the data, I don't think that this is really the main challenge. And there's also a lot of research on it. It calls Trustworthy AI, and it's also funded by, I guess, Horizon 2020 or so. So a big research field. I think there's more the challenge how to preserve the semantic connection between the data without having the problems like Ursina is talking about, these, which language are we using? And therefore, I would say that my claim is that we need to elaborate on these graphical modeling languages to formalize the knowledge, and additionally keep links from the real data format. So let's say there's a CSV file to the formalized knowledge on what is the purpose of the data or from where is it originating. And additionally, how can I connect the data from one machine in a causal manner to another machine. Let's think in a shop floor, for instance. You're designing something, it's prepared in the first step. 2 weeks later, I'm measuring the results. How can I connect these things? And I guess there is a real big effort that is needed for formalizing these things. That's the only way I can see that it could work in 10 years with data from today.
Thank you. Insightful, I think. So, I mean, we're about to round this up. Thank you, the presenters, for sharing the insights on your papers. And I hope people have downloaded them and also reading them. And also thank you for taking part in this discussion. Also, there are 30-something people joining and watching this session. So by that, I wish you a continued good conference and thank you for taking part. Bye-bye.
Thank you. Bye.
See you. Goodbye.